If you keep an eye on CPU utilization of your computer, you will see that the QEMU process now continuously keeps the CPU busy. Oh, interesting. This happens because our simple executor polls tasks over and over again in a loop, right? So even if we don't press any keys on the keyboard, the executor repeatedly calls polls on our print key presses task, even though the task cannot make any progress and will return poll pending each time. I thought that's why we had a waker though, right? Executor with waker support. To fix the performance problem, we need to create an executor that properly utilizes the waker notifications. This way, the executor is notified when the next keyboard interrupt occurs, so it does not need to keep polling the print key presses task over and over again. Task ID. The first step is creating an executor with proper support for waker notifications. First step in creating an executor with proper support for waker notifications is to give each task a unique ID. This is required because we need a way to specify which task should be woken when we start by creating a new task ID wrapper type. Okay. So in here, we'll do this. I'm going to derive a whole bunch of stuff. Clone, copy, and struct task ID. Interesting that it's not pub. Does making it like this, is this the equivalent of making it private to the whole sub? Yeah. That makes sense, right? This whole sub-module, this whole task sub-module. The task ID struct is a simple wrapper type around U64. We would derive a number of traits for it to make it printable, copyable, comparable, and sortable. The latter is important because we want to use task ID as a key type of the B-tree map in a moment. To create a unique ID, we created a task ID new function. Core sync atomic U64 and ordering. Oops. There we go. Impl task ID. Atomic U64 is atomic U64 new. So atomic U64 is, based on my knowledge of OS, I don't know this for certain, but based on my knowledge of the way OSs work, this is just an access to a way to get and set variable or values in memory atomically without needing a mutex. It's slower than a normal memory read or write because it has to guarantee atomicity, but it provides a method of doing it without a mutex, which is, I think, the key thing that they're going for here. Next ID, fetch add, one ordering, relaxed. And that's it. Let's put a space there, cargo check, and of course it fails. What did I do wrong? Oh, this should be dot. And that should be partial ord. And this should be task ID. Wow. Same here. Okay. The function uses a static next ID variable of type atomic U64 to ensure that each ID is assigned only once. The fetch add method atomically increases the value and returns the previous value in one atomic operation. This means that even when the task ID new method is called in parallel, every ID is returned exactly once. The ordering parameter defines whether the compiler is allowed to reorder the fetch add operation in the instructions stream. Since we only require that the ID is unique, the relaxed ordering with the weakest requirements is enough in this case. We can now extend our task type with an additional ID field. Okay, so we did one and now we're going to do two. Oh, that's right here. So we have future, and we're going to put the ID task ID. And then here, we're going to say ID is task ID new. And that fails because I keep doing that. Okay. The new ID field makes it possible to uniquely name a task, which is required for waking a specific task. The executor type. We create our new executor type in the task executor module. Oh, now we're going to add a new module. Pub mod executor. Grab that. And this is going to be use super task and task ID. Alloc collections B tree map and sync arc. Nice. Task waker cross beam queue. So we've seen most of these before, right? B tree map is new, but I mean that's just a B tree map. That's a normal one. Pubstruct executor tasks. Mapping a task ID to a task queue. Task ID. And then waker cache. So B tree map of task ID to waker. So I guess every task can only have one waker. That makes sense, right? Pub fun new self tasks B tree map new. This is almost all default, right? Except for task queue. And I guess we're limiting the number of tasks we can have to 100. Or the number of active tasks, right? What did I get wrong here? I did something wrong. Oops. Oh, maybe this? There we go. Okay. Instead of storing tasks in a vec deck like we did for our simple executor, we use a task queue of task IDs and a B-tree map named tasks that contains the actual task instances. The map is indexed by the task ID to allow efficient continuation of a specific task. The task queue field is an array queue of task IDs wrapped into the arc type that implements reference counting. Reference counting makes it possible to share ownership of the value between multiple owners. It works by allocating the value on the heap and counting the number of active references to it. When the number of active references reaches 0, the value is no longer needed and can be deallocated. We use this arc array queue type for the task queue because it will be shared between the executor and wakers. The idea is that the wakers push the ID of the woken task to the queue. The executor sits on the receiving end of the queue, retrieves the woken tasks by their ID from the tasks map, and then runs them. The reason for using a fixed size queue instead of an unbounded queue such as seg queue is that interrupt handlers should not allocate on push to this queue. In addition to the task queue and the tasks map, the executor type has a waker cache field that is also a map. This map caches the waker of a task after its creation. This has two reasons. First, it improves performance by reusing the same waker for multiple wake-ups of the same task instead of creating a new waker each time. Second, it ensures that reference-counted wakers are not deallocated inside interrupt handlers because it could lead to deadlocks. There are more details on this below. To create an executor, we provide a simple new function. We chose a capacity of 100 for the task queue, which should be more than enough for the foreseeable future. In case our system will have more than 100 concurrent tasks at some point, we can easily increase the size. Spawning tasks. As for the simple executor, we provide a spawn method for executor type that adds a given task to the tasks map and immediately wakes it by pushing its ID to the task queue. Task ID is task.id, self tasks insert sum. Otherwise we do self task queue, push task ID, expect queue full. So if we fill our queue, we just panic. Semi. Okay. Oops. There we go. If there's already a task with the same ID in the map, the btree-map insert method returns it. This should never happen since each task has a unique ID. So we panic in this case since it indicates a bug in our code. Similarly, we panic when the task queue is full since this should never happen if we choose large enough queue size. Running tasks. To execute all tasks in the task queue, we create a private runReadyTasks method. Oh, and then we have to add in a core task context and poll here. This takes a mutable reference to self. It doesn't return anything. Let self tasks task queue waker cache is equal to self. That's just a destructure. Okay, while let okay task ID pop. Task ID some task is task. None is just continue. Got to spell this right. Semicolon. Nope, still not good. What do I got wrong here? This looks right. Oh, there's a semicolon there. That's why. There we go. That's better. Okay, so why that? And then let waker equals waker cache entry task ID or insert with task waker new task ID task queue clone. Let mute context is context from waker. This is just like the simple executor, right? We did the same thing. And match task poll. Mute context. It's poll ready. Task done. Remove it and it's cached waker. Task ID. Okay. Otherwise, if it's poll pending, we do nothing. And I messed this up here. That's better. Okay. The basic idea of this function is similar to our simple executor loop. Sorry, simple executor. Loop over all the tasks in the task queue, create a waker for each task, and then poll it. Okay. Yep. However, instead of adding pending tasks back to the end of the task queue, we let our task waker implementation take care of adding woken tasks back to the queue. We got double of here. The implementation of this waker type will be shown in a moment. Let's look into some of the implementation details of this runReadyTasks method. We use destructuring, right, to split self into its 3 fields, and to avoid some borrow checker errors. Namely, our implementation needs to access the self task queue from within a closure, which currently tries to borrow self completely. This is a fundamental borrow checker issue that will be resolved when RFC 2229 is implemented. Has it been? I don't know. Closures will capture individual fields and not the whole struct when possible. I don't know if it's been implemented yet. Let's take a quick peek over here. Tracking issue. I don't know if it's... Oh, it says closed. Does it mean it was closed accepted or closed rejected? It's stabilized. Stabilization proposed here. Okay, so maybe we don't need to do that anymore. But I mean, it makes the code a little more readable, not having to put self dot everywhere. So for each pop task ID, we retrieve a mutable reference to the corresponding task from the tasks map. Since our scan code stream implementation registers wakers before checking whether a task needs to be put to sleep, it might happen that a wake up occurs for a task that no longer exists. In this case, we simply ignore the wake up and continue with the next ID from the queue. Okay. To avoid the performance overhead of creating a waker on each poll, we use a waker cache map to store the waker for each task after it has been created. For this, we use the btreatmap entry method in combination with entry or insert with. It's here. To create a new waker if it doesn't exist yet, and then get a mutable reference to it. For creating a new waker, we clone the task queue and pass it together with the task ID to the task waker new function implementation shown below. Since the task queue is wrapped into arc, the clone only increases the reference count of the value, but still points to the same heap allocated queue. Note that reusing wakers like this is not possible for all waker implementations, but our task waker type will allow it. Okay, so we're going to have to create a task waker. The task is finished when it returns poll ready. In that case, we remove it from the tasks map using the remove method. We also remove its cached waker if it exists. Waker design. The job of the waker is to push the ID of the woken task to the task queue of the executor. We implement this by creating a new task waker struct that stores the task ID and a reference to the task queue. Okay. And we impl task waker fn wake task self task queue push self task ID expect task queue pull. We still haven't written new. Okay. Since the ownership of the task queue is shared between the executor and wakers, we use the arc wrapper type to implement shared reference counting ownership. The implementation of the wake operation is quite simple. We push the task ID to the reference task queue. Since modifications of the array queue type only require to share reference, we can implement this method on self instead of on mute self. The wake trait. In order to use our task waker type for polling futures, we need to convert it into a waker instance first. This is required because the future poll method takes a context instance as an argument, which can only be constructed from the waker type. While we could do this by providing an implementation of the raw waker type, it's both simpler and safer to instead implement the arc-based wake trait and then use the from implementations provided by the standard library to construct the waker. The trait implementation looks like this. So we need to add task wake here. And then we need to impl wake for task waker. Arc self. Just self wake task. And then fn wake by ref. Self wake task. So the new function still doesn't exist. That's fine. Since wakers are commonly shared between the executor and asynchronous tasks, the trait methods require that the self instance is wrapped by the arc type, which implements reference counted ownership. This means that we have to move our task waker to an arc in order to call them. The difference between the wake and the wake by ref methods is that the latter only requires a reference to the arc, while the former takes ownership of the arc and thus often requires an increase of the reference count. Not all types support waking by reference, so implement the wake by ref method is optional. However, it can lead to better performance because it avoids unnecessary reference count modifications. In our case, we can simply forward both trait methods to our wake task function, which requires only a shared self-reference. Grading wakers. Since the waker type supports from conversions for all arc wrapped values that implement the wake trait, we can now implement the task waker new function that is required by our executor run ready tasks method. Okay, so that's right here. New task ID, task Q, arc array. Oh, another guy in tech in. Thank you for the follow. I didn't hear the alert this time, so I must have turned it way down too far. Much appreciated. Thank you. Arc array Q, task ID, waker from arc new task waker. So this is interesting. The new is not returning a self, right? It's returning a waker. Task ID, task Q. Oh, we don't want to close that one. There we go. And now it builds. We create the task waker using the past task ID and task Q. We then wrap the task waker in an arc and use the waker from implementation to convert it to a waker. This from method takes care of constructing a raw waker vtable and a raw waker instance for our task waker type. In case you're interested how it works in detail, check out the implementation in the alloc crate. I mean, we could always see if jump to definition works. Oh. Okay. That's an interesting implementation of from. Oh, this is just from for that, not from for the actual. Okay. That doesn't help. A run method. With our waker implementation in place, we can finally construct a run method for our executor. So up here, our executor, let's say pub fun run itself, and it's divergent. Ooh, loop self run ready tasks, and that's all it does. It never ends. This method just calls run ready tasks function in a loop. While we could theoretically return from the function when the tasks map becomes empty, this would never happen since our keyboard task never finishes, so a simple loop should suffice. Okay, so it's given for this. But it also means that this is like the beating heart of the OS, right? This is just going to keep doing this until, and if all tasks do end, then that would be an indication that our operating system has come to an end and we should just halt the machine. So that's probably a future enhancement. Oh, MD Gazer says, I think you don't need to destructure if you're using the latest nightly Rust. Yeah, I believe you're right, but it makes the code here a little easier to read. Otherwise, I have to put like self here and self here and self here, right? Everywhere. So it seems like it's easier to read this way. Since the function never returns, we use the bang return type to mark the function as diverging to the compiler. We can now change our kernel main to use our new executor instead of the simple executor. Main. Simple. So we just do that. Oh, and then we have to pull it in here. Like that. And it should do the same exact thing, right? Oh, except we still have a couple of warnings. Unreachable. Oh, now we can't print. It did not crash. We only need to change the import and type name. Since our run function is marked as diverging, the compiler knows that it never returns, so we no longer need a call to halt loop at the end of our kernel main function. Okay. So that means, oh, but test main won't work, right? Okay, so it's already marked as diverging. This won't happen. But how will this run? our tests are not going to run. Well, let's find out what they do. Oh yeah, test main is up here. Okay. Like that. There we go. When we run our kernel using cargo run now, we see the keyboard's input still works. Let's find out. Yep, it still works. Oh, I like that there was a timer interrupt just before the async handler was called. That's neat. Okay. However, the CPU utilization of QEMU did not get any better. The reason for this is that we still keep the CPU busy for the whole time. We no longer poll tasks until they are woken again, but we still check the task queue in a busy loop. To fix this, we need to put the CPU to sleep if there's no more work to do. Sleep if idle. The basic idea is to execute the halt instruction when the task queue is empty. This instruction puts the CPU to sleep until the next interrupt arrives. The fact that the CPU immediately becomes active again on interrupts ensures that we can still directly react when an interrupt handler pushes to the task queue. To implement this, we create a new sleep if idle method in our executor and call it from our run method. Let's get these changes committed. A more complex executor. Here we go. So we have run. We do run ready task and then sleep if idle. Okay. And we create a new sleep if idle. If self task queue is empty, x86 64 instructions halt. Okay. Since we call sleep if idle directly after run ready tasks, which loops until the task queue becomes empty, checking the queue again might seem unnecessary. However, a hardware interrupt might occur directly after run ready task returns, so there might be a new task in the queue at the time the sleep if idle function is called. Only if the queue is still empty, we put the CPU to sleep by executing the halt instruction to the instructions halt wrapper provided by this crate. There's still a gap, right? If it's empty, then we halt. But if it's empty, and just before we call halt, there could be an interrupt that comes in. How do you, Oh yeah, okay, we're talking about it right here. Okay, never mind. Unfortunately, there's still a subtle race condition in this implementation. Since interrupts are asynchronous and can happen at any time, it's possible that an interrupt happens right between the isEmpty check and the call to halt. In this case, the interrupt pushes to the task queue, then we put the CPU to sleep even though there is now a ready task. In the worst case, this could delay the handling of keyboard interrupt until the next key press or the next timer interrupt. So how do we prevent it? The answer is to disable interrupts on the CPU before the check and atomically enable them again together with the halt instruction. This way, all interrupts that happen in between are delayed after a halt instruction so that no wake-ups are missed. To implement this approach, we can use the interrupts enable and halt function provided by the x86 64 crate. The updated implementation of our sleep if idle function looks like this. Okay. So we're going to use x86 64 instructions, interrupts, enable and halt. Interrupts, disable. If it's empty, enable and halt. Else, interrupts, enable. Right. If the queue is not empty, then we want to re-enable interrupts and go back to our run loop. To avoid race conditions, we disable interrupts before checking whether the task queue is empty. If it is, we use the enable and halt function to enable interrupts and put the CPU to sleep as a single atomic operation. In case the queue is no longer empty, it means that an interrupt woke the task after a run ready task. So how does this work? Is there a separate x86 instruction? On some processors, the interrupt shadow of STI just means enable interrupts, right? Set the interrupt enable bit, right? Does not apply to non-maskable interrupts, NMIs. This means that an NMI can occur between the STI and halt instruction with the result that the CPU is put to sleep even though a new interrupt occurred. To work around this, it is recommended to check in the NMI handler if an interrupt occurred between STI and halt instructions. If this is the case, the handler should increase the instruction pointer stored in the interrupt stack frame so that halt instruction is skipped. There's still a time between these two instructions that an interrupt could occur, right? I'm still puzzled how that works. Maybe there's something in the x86 spec that says if a halt instruction follows an STI instruction, the interrupt is delayed until after the halt is executed. That's something to look up. Okay. Now our executor properly puts the CPU to sleep when there's nothing to do. We can see that the QEMU process has much lower CPU utilization when we run our kernel using cargo run again. Possible extensions. Okay, so we're all done, right? Because I see summary down here. So git diff. All we did was add the sleep if idle. Commit add a sleep if idle implementation. I'm going to push that up. I'm going to read through the rest of it, but okay, there it is. Our BlogOS is up to date with the current final entry. Possible extensions. Our executor is now able to run tasks in an efficient way. It utilizes waker notifications to avoid polling waiting tasks and puts the CPU to sleep when there is currently no work to do. However, our executor is still quite basic and there are many possible ways to extend its functionality. Scheduling. We currently use the vecdeck type to implement first in, first out strategy for our task queue, which is often called round-robin scheduling. This strategy might not be the most efficient for all workloads. For example, it might make sense to prioritize latency-critical tasks or tasks that do a lot of I/O. See the scheduling chapter of the Operating System's 3 Easy Pieces book or the Wikipedia article on scheduling for more information. Task spawning. Our executor spawn method currently requires a mute self-reference and is thus no longer available after starting the run method. To fix this, we could create an additional spawner type that shares some kind of queue with the executor and allows task creation from within tasks themselves. The queue could be, for example, the task queue directly, or a separate waiting. I'm gonna send an email and see what's going on, what the plans are. This will make it possible to launch multiple instances of the executor in different threads. The advantage of this approach is that the delay imposed by long-running tasks can be reduced because other tasks can run concurrently. This approach also allows it to utilize multiple CPU cores, right? Each core can have its own thread of execution. Load balancing. When adding threading support, it becomes important how to distribute the tasks between the executors to ensure that CPU cores are utilized. All CPU cores are utilized. Common technique for this is work stealing. Summary. We started this post by introducing multitasking and differentiating between preemptive multitasking, which forcibly interrupts running tasks regularly, and cooperative multitasking, which lets tasks run until they voluntarily give up control of the CPU. We then explored how Rust's support of async await provides a language-level implementation of cooperative multitasking. Rust bases its implementation on top of the polling-based future trait, which abstracts asynchronous tasks. Using async await, it's possible to work with futures almost like with normal synchronous code. The difference is that asynchronous functions return a future again, which needs to be added to an executor at some point in order to run it. Behind the scenes, the compiler transforms async await code to state machines, with each await operation corresponding to a possible pause point. By utilizing its knowledge about the program, the compiler is able to save only the minimal state for each pause point, resulting in a very small memory consumption per task. One challenge is that the generated state machines might contain self-referential structs, for example, when local variables of the asynchronous function reference each other. To prevent pointer invalidation, Rust uses the pin type to ensure that futures cannot be moved in memory anymore after they have been polled for the first time. For our implementation, we first created a very basic executor that polls all spawned tasks in a busy loop without using the waker type at all. We then showed the advantage of waker notifications by implementing an asynchronous keyboard task. The task defines a static scan code queue using the mutex-free array queue type provided by the Crossbeam crate. Instead of handling key presses directly, the keyboard interrupt handler now puts all received scan codes in the queue and then wakes the registered waker to signal that a new input is available. On the receiving end, we created a scan code stream type to provide a future resolving to the next scan code in the queue. This made it possible to create an asynchronous print key presses task that uses async await to interpret and print the scan codes in the queue. To utilize the waker notifications of the keyboard task, we created a new executor type that uses an arc shared task queue for ready tasks. We implemented a task waker type that pushes the ID of woken tasks directly to this task queue, which are then polled again by the executor. To save power, when no tasks are runnable, we added support for putting the CPU to sleep using the halt instruction. Finally, we discussed some potential extensions of our executor, for example, for providing multi-core support. What's next? Using async await, we now have basic support for cooperative multitasking in our kernel. While cooperative multitasking is very efficient, it leads to latency problems when individual tasks keep running for too long and thus prevent other tasks from running. For this reason, it makes sense to also add support for preemptive multitasking to our kernel. In the next post, we will introduce threads as the most common form of preemptive multitasking. In addition to resolving the problem of long-running tasks, threads will also prepare us for utilizing multiple CPU cores and running untrusted user programs in the future. All right, that is that. Oh, TFZ says STI disables interrupts till the next instruction, I believe. Okay, so that makes sense. That's why STI followed immediately by halt means that you don't get any interrupts between those two instructions. Thank you for that, TFZ. But that's going to wrap up my stream, and that actually wraps up the whole series on writing an OS in Rust. We do not yet have a chapter on threads, and I'm hoping that is in progress and will be coming soon. And when that happens, I will make the next entry in this. But for now, I'm going to wrap up my stream.